Greetings, everybody. Let's take a look at the divergence theorem. So just to state the divergence theorem, we've got a piecewise smooth closed surface that is going to kind of enclose some solid E. And we assume that S is going to be oriented outward, so the surface has an outward orientation. And we've got some vector field F that has continuous partial derivatives, and those are going to be continuous on some larger open region that's containing the region that we're actually interested in, our region E. And so the surface S we can really think of as being this boundary of E. And so what the divergence theorem tells us is that if we look at the triple integral of the divergence of F over this entire volume, then that actually pulls back to a surface integral of F dot ds over the boundary of that particular volume. And so what we want to do now is to kind of go through and let's verify the divergence theorem by way of computing an example so we can see how it works if we're computing it in both directions. So computing the left-hand side, computing the right-hand side, and showing it, hey, you know what, they actually do give the same values. And so what we've got is this vector field F with components xz, yz, and 3z squared. And E is going to be a solid bounded by this paraboloid z is equal to x squared plus y squared, and kind of above by the plane z is equal to 1. So for the volume of the integral, if we want to compute the left-hand side, well, for that we need the divergence of f. So remember the divergence of f, the partial with respect to x of the first component, plus the partial with respect to y of the second component, plus the partial with respect to z of the third component, gives us z plus 6z, or 8z. And so what we need to compute over this volume is this triple integral of 8z dv. Well, how do we characterize that volume? Probably the easiest way to do this, since we've kind of got this rotational symmetry around the z-axis, is to fall back and use cylindrical coordinates. And so we'll use our coordinates of x is going to be r cosine theta, y is r sine theta, and z is just going to be z. So if we take our x and y values and plug them into the kind of the boundary for our surface, we get z is equal to x squared plus y squared, which just reduces to z is equal to r squared. So now we're thinking of this as the volume now for this thing. And so if we kind of pick a slice out of this, then for our r values and our theta values, the volume r can go from anywhere from 0 out to the boundary of that surface. And so with that thing, we're just looking at r being 1 for that. Then because we're going all the way around the z-axis, then our theta is going to go from 0 to 2 pi. And then if we're looking at our vertical slices for each one of those things, well, the bottom slice is going to be the bottom of this paraboloid, which is going to be r squared, and it's going to go all the way up to the top of the plane where they're kind of capping this thing off at z is equal to 1. So we get limits of r going from 0 to 1, theta going from 0 to 2 pi, and z going from r squared up to 1. Well, now remember, anytime that we're doing this kind of change of coordinates from x, y, z into r, theta, and z, we got to use the Jacobien to make our dv's balance in that case. And so if we compute the Jacobien, partial x, y, z, partial r, theta, and z gives us a value for r in cylindrical coordinates. And so if we do our integral of the divergence of f dv, we get 8zr dz dr d theta. Z's got to come before r, remember, because z depends on r. So we've got the limit from r squared up to 1, r going from 0 to 1, and theta going from 0 to 2 pi. So nice polynomial that we integrate from that, and we get a nice clean answer of 8 pi over 3 for our volume integral. So now, what happens with our surface integral? Well, for the surface integral, it's a little more complicated because our surface really kind of has two parts to it. Remember that our surface has got to enclose this volume, so we've got the volume below that's going to be this paraboloid, so that's our surface S1, and then we've got another surface S2 that's going to be the top where the plane slices through that paraboloid. And so in both of these cases, it's probably easiest to parameterize these surfaces in terms of our cylindrical coordinates. So for our bottom surface S1, we've got x is equal to v cosine u, y is equal to v sine u, and z is equal to v squared for that particular surface. So now we need to make sure that we have the right orientation. If we check partial x, partial s, partial u, cross partial s, partial v, we get an expression that has this form. Now remember what we wanted. We wanted our normals to be outward facing from the surface. Well, if we look at kind of what would be the r components for this thing, radially outward from the z-axis, our x component is positive, our y component is going to be positive. Whenever u is going to be in quadrant 1. So that's going to be enough to tell us, yep, this thing has the outward orientation that we want it to have. So we're good to go with this one as a normal. And so for f on the surface, we had it xz, yz, and 3z squared. Well, we plug in our component functions to that, and so we get v cubed cosine times v cubed sine and 3v to the fourth. So that our f dot ds, when we take the dot product of those two vectors, just reduces down to something as negative v to the fifth power du dv. And so what happens there when we do our surface integral over S1 of f dot ds, we've got our integral from 0 to 2 pi, 0 to 1 of negative v to the fifth du dv. And so that ends up giving us the answer of a negative pi over 3. Now we turn to the second surface. So we've got our second surface, the top of that thing, where again, kind of using the same coordinate system that we can parameterize it with. So we've got x being v cosine u, y being v sine u, and now z is just going to be 1 because it's just the top of that plane. And so we've got u going from 0 to 2 pi all the way around the z-axis, and our radius going from 0 out to 1. If we look at partial s, partial u, cross partial s, partial v for this one, now we get a result of negative v in the z direction. Well, this is not the outward pointing one that we want. So since we want our orientation to be outward pointing, we take our ds as just being, we just change the sign of that one and make it v in the z direction dA. So that on our surface, if we plug in our coordinate functions, we get values of v cosine u, v sine u, and 3. And our f dot ds just ends up becoming 3v dA. So that our surface integrals just become a nice, simple form. Integral 0 to 2 pi, 0 to 1 of 3v dv du, which just gives us an answer of 3 pi. Now if we turn around and put all of this together, if we look at our interval over our closed surface for our boundary of E, that's going to be the sum of our two integrals. So we've got a negative pi over 3 plus a 3 pi. Well, that certainly does give us an answer of 8 pi over 3, which was exactly what we got for our triple integral of the divergence of that vector field. So this kind of gives us a verification in one example that the divergence theorem does actually work. Kind of lets you see the nuts and bolts of how you go through a concrete example and work through each one. So sometimes it might be easier to compute the divergence of the vector field and then do the triple integral. Sometimes, depending on what the field is, our surface might be extraordinarily easy to parameterize, and so the surface integral might be easier to use. Just depends on the situation. and kind of what we're asked to do. But here we've kind of gone through both sides so you can see the ins and outs of doing both. I hope this has made sense to you, and I will see you guys next time.